Hey everyone, welcome to another episode of Calculus. We're starting chapter 6, which means we're on the dinosaur chapter for my class, anyways. And in this one, this is a little bit of a geometry lesson sometimes, but we are going to be looking at the area under curves and as they relate specifically to rate functions. And you'll see that there is an idea of an accumulation of a rate. So let's start off on the next page and we'll get started with our chapter 6. How about that? As I'm speaking to you now, it's probably really doubtful that you've never heard of Jurassic Park, any of the Jurassic Park franchise pieces. But Jurassic Park and Jurassic World, of course, are a science fiction media franchise, and they are centered on the disastrous attempt to create a theme park with cloned dinosaurs. The entire project began in 1990 when Universal Pictures and Amblin Entertainment, which is Steven Spielberg, by the way, bought the rights to the novel by Michael Crichton before the book was even published. The book was very successful, and as was Steven Spielberg's 1993 film adaptation. I can't imagine anyone not having seen Jurassic Park at this point. Even though the film is getting almost to be 20... No, my gosh, 27, almost 30 years old now. Anyways, in 2018, the film was selected for preservation by the U.S. National Film, so this is a culturally, historically, or aesthetically significant piece of work. We're going to be looking more at the dinosaurs right now than the Jurassic Park. So the first dinosaur we're going to look at is the Gallimimus, and in our imaginations, we've got a flock of the theropod Gallimimus. An observation of that flock was done to ascertain the running speed of, quote, chicken mimic. If you didn't notice it, Gallimimus comes from Latin for chicken and mimic or mime. One observation found a Gallimimus maintaining a 27 mile per hour or 37.6 feet per second, running for 22 seconds. So the first problem, we're supposed to graph this velocity curve, and the idea or the thing I want you to start thinking about is the units. Look at this. This is in feet per second. So if this is in feet per second, the correct thing we should be graphing is not that 27 miles per hour, but that 39 feet per second. Also notice that on the horizontal axis, we have seconds. So let's just take a few measurements here. At t equals 0, if the Gallimimus is maintaining at 39.6 feet per second, then the velocity at t equals 0 is 39.6. Maybe right around there. How about at t equals 5? Yeah, that's also 39.6. T equals 10, still 39.6. 15, still 39.6. All the way to 22, still 39.6. So when we connect that, what does this velocity graph look like? Yeah, that should look like a horizontal line that stops abruptly at t equals 22. When considering the coordinate axis, your graph should be a shape of a rectangle. So, do you see the rectangle? Let me highlight the rectangle if you don't see the rectangle. If you didn't see that rectangle before, I'm pretty sure you see the rectangle now. So, what are the side lengths of the rectangle? Well, the horizontal length here, that is 22 seconds. And the vertical length here of this rectangle, that is 39.6. feet per second. And I'm going to take this opportunity to write feet per second with a slash in it. So we have all that. So what is the area of the rectangle? So the area of the rectangle is 22 multiplied by 39.6, 871.2 feet. Notice how the units cancel. We have feet per second multiplies with a second, and that just gives us feet. Which means that if we find the area and the units match each other, then that unit of time is always going to cancel out when we find the area. So how far did this Gallimimus travel? Well, let's just take this in the algebra approach. Distance is equal to rate times time. Our rate was 39.6. Our time was 22 seconds. And look at that. Isn't that the exact same calculation we just did? 871.2 feet. Yeah, that's the same calculation. So this is confirmation of this idea, that the net distance traveled, that's how far the Gallimimus traveled, that's going to be the same as the area under a velocity curve. Now, velocity is a rate. And remember, a rate is equal to some unit per unit time. It just so happens this time our unit is a unit of distance. So distance unit per time unit. Well, it doesn't have to be distance unit. I mean, it could be another unit with respect to time. And in our next problem, the Roseland apartments are filling their new water tower using an old water pump. The rate at which the water is being pumped into the tank is shown by the linear graph below. How much water is pumped into the tank during the first 24 hours? Okay. Notice that the rate is in gallons per hour, and the unit for time is hours. So whatever area I get, we're going to be multiplying gallons per hour multiplied by the unit of hour, and our answer is going to be in gallons. That's kind of confirmation that we should be really finding the area of underneath this rate curve. So this is where the geometry comes in. Let's take a look at the shape of this curve. Now I know that we're going to cut off the area here at 24 because we're doing the first 24 hours. And here is my shape. And if you turn your head sideways, you should see that this is a trapezoid. This is base 1, this is base 2, and this is the height of the trapezoid. Okay. Trapezoid is any geometric shape that has two parallel bases, or one pair of parallel bases or more. What was that sound? Hey, let's find the area of this trapezoid. So the area is equal to 1/2 base 1 plus base 2 multiplied by the height. So the area here is equal to 1/2. Let's get base 1 and base 2 into the calculation. And then let's get the height, 24 hours. And go ahead and use a calculator and see how many gallons we get. 4,512. I always like to impress upon you that you should be writing a summary statement. So let's write a summary statement. This is pretty easy. We have, if the question is how much water is pumped into the tank during the first 24 hours, we're going to try to mimic that in our answer. Gallimimus again, mimic, huh? 4,512 gallons of water are being pumped into the tank during the first 24 hours. Now, something that I also want to impress upon you is, as a calculus student, you need to be writing things in terms of equations at this point. Notice how there's an equal sign in all of the mathematics that we did. And the equal sign is going to connect the concept of area with the formula. It's going to connect the concept of area with the number 4,512. So that 4,512, the next logical leap is to say the 4,512 is the same thing as the number of gallons of water pumped into the tank. And that's all of the work we're doing today. There's an important ideas box. Let's see which important ideas I came up with. So no real mathematics here in the important ideas. This is very conceptual. The idea is that a rate function is a function whose outputs are given as something per unit time, like miles per hour or gallons per second. When graphed versus the correct time unit, the area under that curve is going to give the amount accumulated, like how many miles were accumulated, how many gallons were accumulated during that time period. Area under the curve then really is the same thing as the amount of the accumulation. That sounds like the same thing twice. It kind of is, but it's kind of not. And finally, where we are with calculus, we're just going to use geometry to find the area under the curve for most functions. And I think at this point we should take a look at our check your understanding. We have another dinosaur, a Parasaurolophus, named P38NT, is accelerating at a constant rate from 15 to 24 miles per hour for 1 minute and 12 seconds, or 0.2 hours. How far did P38NT run during this time? Hint, the velocity curve is linear. Let's take a look at that velocity curve. Notice that we have to pick our correct units again. We are given a rate in miles per hour. And so this unit right here, 112, that is kind of useless for us. The unit that we want is hours. And if we didn't get that hours, we would have to have converted that to hours. Okay, conveniently, the graph says hours already down here, and it says miles per hour over here. So we're starting at 15 miles per hour. So we're going to put a nice juicy dot at 0.15, which is here. And we're going to go to 24 miles an hour once we get to 0.02 hours. 24 miles an hour is, that's just right about here. So, and then of course, it's going to be accelerating at a constant rate, so we're going to get a straight line function. Let's draw our straight line. There's our area, and we're taking miles per hour. We're going to be multiplying by hours, and that's going to be equal to, of course, hours. Miles. So the distance traveled is going to be equal to, maybe I should write the word distance. That's going to be equal to area. The area is 1/2 base 1, 15, plus base 2, which is 24 miles per hour. Let's write those, 15 and 24, multiplied by 0.02 hours. So this is 0.02 hours from here to here. And let's figure out what that is. Our mathematics tells us that the distance run by the Parasaurolophus was 0.39, and now we just need a summary statement. So our Parasaurolophus ran 0.39 miles during the 0.02 hours, or basically during the 1 minute 12 second time interval. So that's it, everyone, with our 6.1. A very nice and easy start to our next chapter, chapter 6 here in calculus, and we'll see you next time. Have a good day.